Hi, my name is Felix Martillo in the UT Dual Enrollment Engineering class, and today we're presenting my reverse engineering presentation for the race car flashlight. As we know, this is the original PIG flashlight that we were going to be reverse engineering. So the first thing we had to do was we interviewed potential customers to get our top 5 needs, which was the light quality of the flashlight, the on-off switches that you use to turn the light on and off, and also the back one to lock the crank in place. The grip of the flashlight, some people thought it was a little bit too slippery. The size, some people thought it was too small, some people thought it was too big. And then the durability, they thought it broke too easily. So after this, we did our benchmarking. So we tested the flashlight to get specific quantitative numbers. So the first thing we did was we tested the durability of the tail connection. Basically, we used a force sensor to see how much force was required to break the tail. It required almost 31 units of force. We did the same thing with the body. We basically just pressed down on it until it broke with about 58 units. Then we measured the handle, which was another area of concern. We measured the circumference of the handles to see how it would fit like in your hand, and it was 12.5 centimeters. The grip, it only required about a quarter of a Newton to break the force, static friction. So we knew we could make that a little bit more to have more grip. The light quality, we were only getting 770 lux at 1 centimeter, and even less as we moved farther, 250 at 30 centimeters. The on-off switch, some people thought they were too small, so we took a measurement and they were 1.5 centimeters in length, and the on-off switch was 1.5 centimeters in length, and the lock switch was 1.2 centimeters in length. And also, the on-off switch required 6.8 units to slide, and the other one required 13.1 units. Also, the size of the flashlight, almost 11 centimeters in length, 10.8, 4.8 in width. That's with the crank closed. With the crank open, it was 6.9 centimeters in width, and the height from the bottom to the top was 3.9 centimeters. So this is what the inside of the flashlight looked like, which is with the gears and everything, the crank, the wires, and the flashlight, the light coverings. Then we got our black box model, which is basically how the energy is flowing through the system and through the flashlight. So first, we get human energy, which is the input. It goes to the lever, from the lever to the gear, using mechanical energy, mechanical rotational energy. And that generates also noise and heat. And then from the gear, we get to the magnet coil, which again is rotational mechanical energy. We'll also get noise and heat. From the magnet coil, we go to the wire, electrical energy. We get a little bit of noise and heat. And then from the wire to the LED bulbs, electrical energy, now we're just getting heat. From the LED bulbs to the lenses, light energy, and again, heat. And the final output is light energy. So this is how the flashlight is working on the inside. So we determined that we needed to fix this flashlight. It was not our best for our customers. And we came up with our new idea, which was the race car flashlight. It's a race car, it's a flashlight, it's a keychain. It's new, it's here, and it's now. The way we came up with this idea was honestly, my group was 4 boys, and boys will be boys. We were just playing around with the flashlight like it was a race car, and we thought, hey, why should we make this a race car? So this is how it's gonna look on the outside. These headlights right here act as where the bulbs will be, and this is where the light's coming out of. It's gonna have wheels so it can actually move along. It's gonna be 10 centimeters in width. 6 centimeters in width, 10 centimeters in length, and 3 centimeters in height. This is how we want the light sign to look like. So it's somewhat similar to the PIC flashlight because we decided that we wanted to change the flashlight in the simplest way so we can keep it cheap and still effective. So again, you're gonna have 8 LED bulbs with a AAA battery. We're still gonna keep the gears. The only different part is that instead of actually using the lever to turn the gears, we're gonna use the keychain sort of like as a pull, like you would a lawnmower to start it up. And the actual cool part about this is that we're not saying this flashlight is rechargeable, but instead we're gonna use it to simulate race car actions. So when the race car goes to the start line, you pull the crank to rev the engine, which is where that noise comes, or this is where that noise is supposed to be. And the flicker of the lights when you pull it is that car flickering its lights to get ready to race. And that's how you know it's gonna leave all the other race cars behind the dust. So we got our design specifications, which are the performance targets and constraints of our new design. So on the inside, we want a more efficient gear ratio. The big gear is gonna have 85 teeth, the smaller gear, 10 teeth. We're gonna have a lighter magnet, 5 grams, so it can spin faster and give a more powerful flicker of those lights. Then again, we're gonna have 8 total LED bulbs to have a 1,300 lux of brightness at 1 centimeter, making the camera more bright, which is one of our top needs. Those on-off switches are gonna be a little bit slightly longer, 2 centimeters long, and only require 5 newtons of force to slide. We're gonna have a little bit more grip, so it's gonna be 0.5 newtons required to break the surface friction, and it's gonna be able to withstand 750 newtons of force, which is about the weight of an average human. The body length is gonna be, as said, 10 centimeters in length, 6 centimeters in width, and 3 centimeters in height. And basically, we want this flashlight to be more customer friendly. We're gonna make it meet the needs, and we're trying to keep it as cheap and as efficient as possible. Thank you.